Hi and welcome to video 10, unit 4, topic 1, second derivative in math methods, and we're looking at another optimization question using measurement. So in example 10, we have a triangle inscribed inside a semicircle of radius 10 centimeters. Find the minimum area of the shaded region. So we have a couple of methods here. The first method involves the fact that in specialist maths, there is a proof to show that any triangle within a semicircle has a right angle here, and that's going to make our life a lot easier. The second method, we should be able to do it by dropping a perpendicular line down here, which is how we prove that semicircle rule anyway, and then going through the same process. So what I'm going to use is the first method. I know it works, and you're probably given some sort of information like this in the exam because it's a little bit tricky, the second method. So let's assume we're told that that's a right angle. Now I'm going to set this up by starting to think about, well, I want to find the minimum area of the shaded region. So because I want to find the minimum area, I'm looking for area equals something. Now we're talking about the shaded region. So let's take time to think about this objectively. To minimize the shaded region, we really want to maximize the area of the triangle. So the area of the shaded region is going to be equal to the area of the semicircle minus the area of the triangle. Now the area of the semicircle is pretty easy. The area of the semicircle is equal to half pi r squared. And in this case, we're told the radius is 10, so therefore that's going to be equal to 50 pi, whatever that is. It's the area of the triangle that's trickier. So let's talk about what we know with regard to the triangle. And to do this, I might just move this stuff down a little bit. Now, in the triangle, we have a base length, well, this is 10, and this is 10, and therefore we have a base length of 20. And that, of course, is the hypotenuse. But the hypotenuse doesn't do much for us in terms of finding an area. Instead, if we wanted to find the area, what we would do is calculate using two side lengths of a right angled triangle, and the area of the triangle would be equal to a half x times y. And so therefore the overall area of the shaded region is equal to 50 pi minus a half x times y. But we also have another relationship because we need to eliminate either x or y. So let's use that other relationship, and that is that x squared plus y squared is equal to 20 squared, which means that in either case, and let's say we eliminate the y because that's the natural thing to do, y is equal to the square root of 400 minus x squared. There's no easy way this time. We don't have an x squared or a y squared to eliminate as we have done in some previous questions, so I need to introduce a square root function, and about time too. So the area is equal to 50 pi minus a half x times the square root of 400 minus x squared. Now I'd like to just quickly mention, in terms of, my apologies, let's just skip down. In terms of what we've done so far, we've got some interpretation here and here, and then we've started to set up our relationships here and here, and this is where we first do that elimination. I should also be defining my variables, which I haven't done, but I'm sure you've seen me do it enough. Okay, so the area is equal to that. I'm going to quickly write this down as 50 pi minus a half x times 400 minus x squared to the power of a half. So it's going to be important because I'm now going to do dA dx, it's going to derive, 55 disappears, and I've got a chain rule question, u and v. So I'll go through this a little bit quicker. My u is negative half x, so that becomes negative a half for u dash times v, which is 400 minus x squared to the power of a half, plus u, which is negative a half x times by 400 minus x squared to the power of negative a half times by a half because I brought the power down and decreased it by 1. Make sure that looks like a half. And then multiply by that by the derivative of the inside, which is negative 2x. And simplify it. And I'm going to write these back as square root functions. So I end up with this negative here, and this negative make that a positive. Also the 2 and the half cancel out, which is handy. I've still got a half floating around here, and I've got 2 x's and some other stuff. So I'm going to pop this one first. This right hand side, because it ended up being positive, I'm going to pop that first. I end up with an x squared on top, which accounts for this x and this x. And then on the bottom, I end up with a 2, which accounts for this half. And I end up with, because this is a power of negative a half, I'll end up with 2 square root 400 minus x squared. And then my second one, which is negative, becomes negative a half square root 400 minus x squared. So that's a positive a half. So that stays on top. And I've got this half here. So I've got this factor 2 on the bottom. Now, I'm going to let dA dx equals 0. And I've started doing some index laws work, some pretty intense index laws work, and it's going to continue. So if you need to go back and review index laws, please don't be afraid to do so. So I'm going to have 0 is equal to x squared over 2 square root 400 minus x squared minus a half square root 400 minus x squared. And I'm going to multiply everything by the square root of 400 minus x squared. So of course 0 stays as 0, and I end up with a half x squared here. But over here I've got my half, so that's cancelled off at the bottom. But when I do the square root of 400 minus x squared times by itself, by definition of what a square root is, I end up with 400 minus x squared. Because it's like the square root of 2 times the square root of 2 is 2, the square root of x times the square root of x is x, and the same thing here. And then I get that's equal to 0. So now I'm going to simplify this. I'll leave the 0 there for now. A half x squared minus 200 plus a half x squared gives me, I'll pop the 200 over here, 200 is equal to x squared, and therefore x is equal to the square root of 200, or 10 root 2, or about 141 is that value. So that's, I'm going to leave it exact for now because I'm not quite finished, but that's the value I get to for my x. Now if my x is 10 root 2, I can calculate my y and then I can solve this problem. But first it says find the minimum of the area shaded. I've started step 4, and this is kind of the conclusion of step 4. Finding y, or the area, is at step 6, but I need to do step 5 first. And for step 5, typically what I would do now is determine d squared a dx squared equals, now this thing here is dA dx. So d squared a dx squared is the derivative of dA dx, which is x squared over 2 root 400 minus x squared minus a half 400 minus x squared. And this, to me, is sad face. So instead what I'm going to do is I'm going to do a gradient table test. And that's where I go, well, what is 10 root 2? And 10 root 2 is, I may have said 141 before, which is incorrect. 10 root 2 is about 14, or yeah, so 14.16. So I'm going to say, well, I know the gradient at 14.16 is 0. That's why I found that special value. What happens with the gradient at 14 and 15? This is what's going to be important to me here. So there's my x, and here's my dA dx. Now if I do the gradient at 14, and I put 14 into that gradient formula, this one here, it doesn't take too much time. I've got 14 squared is 196, so I get 196 over 2 times the square root of 204 minus a half times the square root of 204. And when I do that, I come out with a value that's slightly negative. Pump it in your calculator if you need to. I do the same with 15. I come out with a value that's slightly positive. And so that means I've got a negative gradient, a 0 gradient, and then a positive gradient, which is, of course, in the shape of a minimum. And so I've got a minimum value here. So x equals 10 root 2 gives me a minimum value. Y will equal the square root of 400 minus x squared, which is equal to the square root of 200 as well, which is equal to, would you believe it, 10 root 2. And therefore the minimum area is going to be, if I go back up to my area formula, my probably best one, I've got x and y now, 50 pi minus a half xy. So 50 pi minus a half times 10 root 2 times 10 root 2, and that comes out as 50 pi minus 100, and that comes out as about 57.1 centimeters squared. And so keep in mind here that this is our best value and the correct answer unless you're asked for decimal places, but there's our answer below in decimal places. All the best.